Yeah. So, welcome to the live session for week 9, the NPTEL operating systems course. The agenda of the live session would be we'll be discussing some questions pertaining to the week 9 syllabus, that is virtual memory and those concepts. The main aim of these live session is that you should make use of these live sessions and clarify your doubts with respect to these week 9 contents, so that it would be helpful while you try attempting the current assignment questions that are released on the NPTEL portal. Okay, so you can either uh, place your questions in the chat box, or you can unmute yourself and speak. So let's get started then. Question 1. Which one of the following is the address generated by the CPU? Is it the physical address, or absolute address, logical address, or none of the above? C. Logical address. Right. Any other guesses? Okay. So the answer given by Nandan, C, logical address, is the correct answer. So one thing to note in this question is they have just asked which one of the following is the address generated by the CPU, and the notion of these logical and physical addresses are meaningful only in the context of MMU systems, as in where you have virtual memory, or there is some so in virtual memory you have the page concept and all those things, right? So whatever address that you are viewing, so if you do see out um, ampersand um, variable, so the address where this variable is stored, so whatever it gets output on the screen, the display value is the virtual address. This is the one that your CPU would generate, and this is where it would actually be stored. But in the actual memory system, this virtual address would be mapped to something known as the physical address via some page tables or segment tables. So this mapping would be done by your MMU, the memory management unit. But in some systems, say you have your embedded systems, um, for example, in washing machines, those embedded controllers and all those things, they typically don't use the MMU, because for every load or store access, right, you're accessing the memory. For every load or store instruction, you should be going through this extra mapping logic in between, and this will drain the resources. And in these embedded systems and all these things, the battery constraint and the memory constraint, all those things should be there. So storage, uh, and then power constraints. So these constraints all would be there. So in these scenarios, they typically don't use the MMU. So in that case, in those systems where the MMU is not being used, there is no concept of physical or virtual address. So it's just like absolute address only. So, so absolute address, as in it's like say for example, some instruction is there, like load A1, some offset value would be present, comma some into some other register. So what it will do is it will add whatever value present in this A1 register, so A1 plus this offset value, and that will give rise to the absolute address. So this would be the only this absolute address would directly be given, used to access your memory system. So there won't be any MMU in between. So in these embedded systems or systems where they don't use the MMU, it's just the absolute address which is being generated by the CPU. There is no concept of virtual or as in logical or physical address. So here virtual, as in I'm just another word for logical address. So it's just like absolute address only. But as far as this course is concerned, and also this week 9, We concentrate mostly on the MMU, memory management unit, and all these things. So in this context, it is assumed that the MMU is present. So in this context, the address generated by the CPU is known as the logical address. So option C is the correct answer based on the assumption that the MMU is used in the system. And just for your info, I just explained like some systems that you don't use the MMU, you have the notion of absolute addresses and relative addresses, but not logical and physical addresses. But as far as this question is concerned, option C is the correct answer. The other options are wrong. So, any doubts in this question? Yes. So it depends on the. So caches are different, right? Like it is invisible to the programmer. So if the embedded system chip or something has the does not have any size constraints or anything, usually they will use caches. So it's
Uh,
up to the chip, what chip they want to use and those things. All
which uses the MMU memory merge system, because is it the system uses or the CPU uses?
I didn't get your doubt, Shashikant.
I mean, who uses the MMU? I mean, MMU change the logical address to physical address, right?
Right. So when your instruction gets loaded into the PC, say instruction I1, which is a load instruction, when this gets loaded into the PC value, it gets executed. So executed as in it will be given to the CPU. The CPU, what it will do is it will generate your it will add the offset with the register and all those things, and it will generate the logical address.
Yeah, I got it. I mean,
Yeah,
I
yeah.
want to know who uses the MMU basically,
So,
because in direct memory interaction,
okay. No,
there is
so
like,
as in the CPU goes and places a request on the MMU, places a request, as in it will have its own format and all those things. So it will place a request like I want 8 bytes of memory from this address, and the MMU will do whatever it needs to be done. So as part of this MMU, there will be the cache, the page table, TLB. So whatever the architectural designer, the
yeah. I mean, so it means the MMU take care of this cache, page table,
yeah,
and TLB,
it
all that,
takes care of
and
everything.
CPU only interact with it, like giving the logical address and that's it.
Yeah, it just adds the offset and those things, and just places the request to the MMU. The MMU has to efficiently manage these locations and all those things.
What happens in DMA? I mean, direct memory access.
Direct
In D,
memory access, right?
yeah. I mean, when CPU don't interact in this all, I mean, memory management, like uh, when the memory is accessed by directly by that. So MMU
Right.
does this thing.
So that's a nice question, Shashikant. So as far as I recall, right? So direct memory access, the concept is for reaching you should not go through via the CPU. The I/O device is given control of the memory, and the thing is, I'm not very sure, but it handles the physical addresses directly.
So does it happen through MMU or?
It happens through the MM. So there will be a separate DMA controller or something. So the
Okay.
MMU is with respect to the CPU. The CPU places the request and all those things. In direct memory, in this case, right, the memory management unit, it will have access to the cache, page table, and TLB and all those things. This so as in to answer your question better, right? The cache will have a cache controller, so every component will have its own controller. So there will be a TLB controller, and there will be a page table controller, like managing those things. And also for the DRAM, there will be a separate DRAM device driver or like controller, which is used for interfacing. So the MMU will interact with these controllers, and this DMA controller is specific to your main memory. That's a DRAM only. So it don't
Okay.
go via the MMU. It will go via the DMA.
Thank you.
And also since you asked this question, right, since the DMA is directly using physical addresses, there has been changes like recently, since not sure, like recently as in the past 5 years, since the DMA is using physical addresses directly, the notion of process abstraction. So the one important advantage of using virtual memory is security. So you are able to the uh, uh, split the process space, right? You are able to isolate the process space. So security is one important advantage of using this virtual memory. But this DMA, if say a process gets access to a DMA, it can just directly give out any physical address, and it can try to read the contents if the security policies are not kept in place while accessing the DMA. So, for example, if some IO device or something is say like process P1 requests this IO device to transfer some memory, and this IO device has to just get the the values present in the process P1's pages only. But if the IO device is corrupt or something, if it's like some vulnerability is present, the IO device can misuse this DMA power to generate any physical address and access the other pages which are allocated to other processes like say P2 or P3. It can use the DMA. Via this DMA it can access those pages. All the checking and all these things, the security policies as in the page table, the mapping and all these things will be is present in the MMU only. The DMA is not uh, that does not know about these policies at all. So in this case, there
Okay.
is a security vulnerability. So in recent systems, what they have done is they have introduced the concept of IO MMU. As in the same MMU concept, they have extended this to DMA also in order to make it more secure. So this just for your information I'm telling.
Okay. Thank you. Thank you very
Yeah,
much.
cool. So coming back to Nandan's question, he had asked whether embedded systems use caches. It depends on the scenario. So they can just directly use like a fast, the main memory itself. They can just implement in SRAM or something, and for faster access if it's very small, or they can use caches. So that nothing stops an embedded systems from using caches. It's for performance and optimization only, right? So it doesn't stop. Um, we can use caches. That's not an issue. So if there are no more doubts in question one, let's move to question two. What's the swap space in the disk used for? Is it used for saving temporary HTML pages, or is it
He is
used for?
saving
Sorry,
process bus.
right. So Shashikant has mentioned option B, right. So storing the super block or storing device drivers. Oh. So the correct answer is option B, which Shashikant had mentioned. The other options are wrong as in, so this is just like some random data. It can be anything, so it's just like a confusing option. Storing the super block, it's not correct, so this is something to do with your underlying disk and storage device or something. And storing device drivers is nothing but storing your code only, so this is also just a confusing option. So the other options are wrong. um, the main thing of swap space in the disk is like the process data and all those things as a live memory. Whenever the main memory does not have enough space to handle all the active processes, then it uses the swap space, and that's the main utilization of this swap space in the disk. So, any doubts in this question? Right. Yes, Nandan.
Hello,
Yeah.
can
Yes.
you hear me?
Yeah. Yeah. I can hear you.
Yeah, like I have a question with the memory. Like, if we use the swap memory, does it incur any additional latencies?
Um,
Like, if I
yeah.
have a 4 GB RAM
Okay.
and if I want to add 1 GB swap space, uh, after adding, will I get any latencies accessing the swap space?
I
So,
feel that
no,
space is different than
that
RAM space.
the sorry, Sashikant. Can you?
I feel that swap space is different from RAM space. Like,
Yeah, yeah. So, uh, based on my stash space is something you store it in the disks, right? So, you have the RAM, that's your secondary memory, and sorry, primary memory, right? That's your primary memory, and then lower comes the storage system or disk. That's your secondary memory, and the swap space is meant for present in this disk only, your hard disk, right? That's where the swap space is stored. It's not part of your main memory or the RAM.
so it will have that, latency
Yeah.
or something, because you
So
have to go back to disk and
yes, whenever you access the swap space, there will always be a latency. It's just meant to, like, you're reserving some part of the disk so that the OS as knows the contents in the swap space, and say like you have hundreds of 100 processes that are actively running, and your RAM can just can just store 99 of them. So the remaining one process you have to store it in the swap space, and say whenever you have to schedule it or something, when you have to put it in the ready queue or something, then you bring the other process and swap it with some other process like that. So that's why the swap space is used. Does that answer your question, Nandan? Right. Yeah. So in that case, let's move to the third question. Which register holds the smallest legal address of a program in memory? Is it the base
base
register or
base
count?
register.
Right. So the correct answer is the base register. The other options are wrong because count register is nothing but it's like a general purpose register, right? You have the CX register, if I'm correct, in your x86 process, so that's like a count register. And the limit register is used in along with the base register in order to have a limit on the range that is accessible by that segment or in that process. So that's what the limit register. So option A is the correct answer. That's base register. So finally, the base plus your whatever offset you are using uh, should be less than your limit, and if so, then the offset plus base would be added to get your address, the actual address. Any doubt? Yeah,
This overflow, that condition of overflow happens when we cross the limit, right?
the condition of overflow. I didn't get it. What condition did you mention?
Your memory overflow condition, when it happens, because
So are you asking overflow? Okay, so there is something called a buffer overflow in
what
section.
happens is somehow we cross the limit. I mean,
No,
whatever.
so if this No, so if these checks are like embedded in, usually it would be embedded in as part of the hardware rule itself, right? So it's not part of your OS or some. So it will be part of the logic would be part of your CPU itself. So in that case, you can't easily like cross this limit and go. Um, there can't be any overflow in the normal case, unless you know, say say some attacker gets access to the OS kernel itself, and he changes the base values of the segment. He corrupts the base values, corrupts the
Yeah,
base of.
that's what I'm asking, because
Yeah, so
what
in that case only, in that case, if the base and the limit values are corrupted by the attacker or something, or not an attacker, say some error or some logic error in your OS system or OS, then the segment would be accessing some other memory other than it was supposed to access.
so that overflow condition is different. I mean, this doesn't happen here too when we
So
access.
overflow. So what do you mean by overflow? That's what I'm. So there is something called buffer overflow in the security
You know,
context.
we have the concept of memory overflow in it.
As in, you require more memory, but just say 4 KB you require, but 1 KB is only allotted. In that case, you're mentioning it.
Okay.
In that case, means the process has to request the OS to provide some more memory, and in that case, the limit would be increased or something like that. It would be shifted to some other memory like that.
Okay. Thanks.
Yeah, and in security concepts, like there is like buffer overflow, as in say you have a main function, and you have like int a of 10, and there is like int b. So a is an array, and b is just like one integer. And now if you just uh, like for int I equal to 0, I less than 11, I plus plus, and you're reading the values of into the array. So in that case, this one is a logical bug over here, as in there should be only 10, there are only 10 elements in the array, but the loop is going for 11 times, 0 to 10. So this a of 10 will also be accessed, but this a of 10 would be actually pointing to this location b. So whatever this b value has, you will be overwriting. So this is like a buffer overflow. So the buffer, you are overflowing it. Only 10 elements it should be accessing. The limit is 10 only, but you are accessing, you are giving the index, the 11th element index to the array, which only has 10 elements. So this giving index 11 is actually you are accessing outside the array, and in that case it's an overflow.
Okay.
And these things all your segment registers can't handle, because everything is within your segment. This variable is within the segment, and the array is within the segment. So this will happen. So if you are referring to this, yeah, it will happen. But beyond the limit, it cannot access it unless they corrupt the OS itself and corrupt the base and limits value. The overflow cannot happen.
Okay.
Beyond,
Got it.
yeah, right. So if no other doubts are there, then we'll move to the fourth question. The address binding of the instructions and data to the memory address, the actual memory address, can happen during when is it the compile time, load time, execution, or all of the above?
I feel it should be all of the B.
Okay. Any other guesses? A, B, C, or D? So the correct answer is all of the above, as Sashikant has mentioned. Um, so in compile time, say for example, even in MMU systems like where there's like virtual and physical memory, the logical and physical address. Say when you're trying to access some specific device or something, the device will be mapped specifically to a physical address. So it will always be present over there. And in that case, you would be directly mapping that using this physical address directly in your code as part of your variables and all those things. So at compile time itself, the binding of those variables to this physical address would be happening. So this is one example for compile time binding. For load time binding, what happens is there are two cases. This is the case of like uh, loading, as in uh, loading before execution, right? So say for example, this is your a dot out, like the executable that you got after compiling, right? And now this a dot out is using some printf function and all those things, printf, scanf, etc. And usually these functions, right, these utility functions would be present in a library called libc, which would be like glibc, which is provided by your compiler toolchain itself, like external to the compiler. This glibc library would be present, and this glibc library would be a shared library, as in it, if you notice, it will be like a .so file, like a shared object. Okay, so this why shared in the sense, this glibc library, this printf, scanf, all these functions would be used by almost all your programs. So instead of having multiple copies of this glibc library, and so for each executable, so this glibc itself would be like, say, so many MB, because it will have printf, scanfs, and all these time and like lots of functions, and it will be huge in size. So just for, say, like printing an hello world program, if you, for every program, if you are having a separate copy of this glibc library, it would consume your system resources. So in order to avoid that, what it will do is it will have a shared library, and the shared library would be linked to all the executables. So if you do like hash include stdio, right? So if you are using some function in your glibc like that, and if you are using the shared library uh, while compiling, if you just if you don't give the uh, option hyphen static, if you don't give this option, then it will by default use the shared glibc library. And now for, say, like you have multiple executables, a dot out 1, a dot out 2, for all these things only one copy, so all these things would be just utilizing this just one copy of this glibc library. And since the variables internal to this glibc library, so within this library itself there will be some variables like global variables and local variables like int a, int b, and all those things. And then and also you would be from this executable you would be calling printf and all those things. So while compiling and linking, you won't know where this printf is exactly located, because it's present outside your executable and it's present in the shared library. So what happens is, when you do dot slash a dot out, this invokes your kernel for creating a new process based on the binary image, the the program set of instructions located in this a.out file. The kernel will do the fork operation and exec, and then what it does is gives control to a loader. And this loader, what it does is it will populate all these exact values, say printf and all these functions that you are invoking in the shared library, right? All these values it will be populating it, because the loader what it will do is it will map this glibc library, this library, it will get mapped into the address space.
I have a question here. I mean,
Yeah, yes.
in programming, that like we use a printf function, or suppose if we are seeing the recursion program.
Okay.
So in recursion, we normally use memory. We use memory stack, right?
Ah,
So that will be considered in load time instruction or execution time instruction.
okay. Memory stack. Um,
There
no.
are multiple
So,
printf functions,
ah,
and it creates a
so
stack.
uh, the stack, right? The stack is execution time, right? Because like stack based address means actually you won't be everything would be relative to that stack pointer via push and pop, and also via some offsets, right? So you won't. So this is like execution time only mostly.
Okay,
Uh,
thank you.
as in address generation is different, address binding is different, right? Uh, so this is like for the data values and for the load and store instructions. For these things you are using with relative to the stack pointer. Um, in this case, like apart from this scenario, right? Even in like shared library or something, in order to call a printf to execute those instructions, you have to know where the addresses have to be, where the functions are present. So for that you have to know the absolute logical address, or at least some based offset or something. So for those things the loader comes into the picture, and it loads all the libraries into the virtual address space of your executable, and then it populates as much as possible. So that's what happens in the load time.
So basically, you can say that load time is for a program, and execution time is for a process.
No, 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 no. That's wrong. So actually, I shouldn't have used the term program itself. Sorry. So when you do dot slash a dot out, your the binary a dot out is actually you are creating a process, right? When you do this command dot slash a dot out, when you are trying to execute a program or this binary a dot out, you are generating a process. The kernel will fork and execute a new process, and then it will give control to your loader. This loader what it will do is it will populate your process address space with the shared library. It will map the page tables and all those things, and also it will have some it will go through some instructions and all those things, and it will fix the addresses of printf function, scanf function, and all these things. So everything the loader has to do is with respect to the process only. At compile time it's the program, so at load time it's the process,
Okay, thank you.
right? And when you come to execution time, say um, uh, uh, you might have been knowing like concept of like dynamic loading. So for example in dynamic loading, one example is uh,
Malloc.
no, malloc and those things are different, right? So yeah, so as in the same glibc library, say you want to use some other library, some custom mylib. So you want to use some custom lib dot dl or something, it will be given the extension. So what happens is within your program itself, you would be using some code like dl open and dl shared, like that. Some functions are there. So what this will do is the main reason of dynamic loading is say this a dot out executable, you're in you're in a huge company and your program is huge, say like it is a web server program you want to execute, right? And what happens is it will have so many hundreds of libraries that it will be using, one for parsing, one for like the IP protocol library, one for the TCP library, like that. So many libraries it would be using. And now, if you create an instance of the web server, the main aim is to have like faster response. Okay, so in that case, if you create a new web server process, and if you invoke your loader, it will load all the 100 libraries before before itself, and then only it will go to the main function, which is part of the starting logic in your web server process. So once after loading all these 100 libraries only, it will go to the main function. So loading will be taking some significant amount of time, and it will reduce the it will have an impact on the response period. So to overcome this, what they do is they will do dynamic loading. So say like out of these 100 libraries, only 20 libraries I'd be using always, like the parsing TCP IP libraries I'd be using always means I will first load just the 20 libraries. First load just the 20 libraries initially, and then whenever the situation arises, say like the user wants is requesting some service based on some graphic processing like image processing, something like that, then based on that service you will dynamically load the extra libraries based on whether the user is requesting that service or not. So in this case, what happens is loading the 20 libraries will be beforehand, you will be doing it, but all these 20 libraries would often be used by your program, so that's why you are loading it beforehand. And then you start continue with your program logic, the web server logic. And now if the user uses some other service and some extra library is required, then it is dynamically loaded. If the user doesn't need that service at all, then you are not loading that library and all those things. So just blindly loading all the libraries would be waste, because just 20 libraries would always be used, and the remaining 80 libraries would rarely be used, or it depends on the user choices. So in these scenarios, all dynamic loading is useful.
Okay, I have a question. Like, if a program has user input interaction, like asking user for some input.
Okay.
So what we are going will you consider in execution time or in load time?
When when the process requests the user for a value, what value is that?
Like, suppose whatever there is a program. I mean, at random it is asking user some giving some value.
Okay.
So will we consider this in execution time memory binding or?
No, just inputting a value does not have anything to do with memory address binding, right? Uh, say you just do like
Suppose,
C.
suppose the program asks for your name, and
Okay.
I'm my name. So my name will be added to some memory address, right? There will be a binding, right?
Right. So if your name is present on, it can be present on the stack, or it can be present on your heap memory, or it could be present in your global memory also. So these are the possible memory regions where your that name variable would be present. So if it's like the heap means the actual address would be decided at the execution time, right? Like once you do the malloc, it returns the address where it is stored. Stack is also like stack. I would say it is load time, because the stack is created when the process is created. That is at the time of loading the process. So once you know the stack address, the base of that stack address, you can, like, theoretically speaking, you can just go through your program and say from the current stack pointer or something, like at an offset of 24 bytes the name variable would be stored like that. It can be like load or execution time, so it depends for the stack.
So
It is execution.
you're saying that stack comes in a load time, right?
Yeah, the stack is created at the load time, the
So
initial
what
stack.
happens in recursive programming? And suppose there are lots of functions,
Okay.
the function is going to repeat, I mean, recursively.
Okay.
So this will happen when the program is actually going to execute, right?
Right. Yes. The stack
So
pointer
how,
will
do-
be
how,
changing.
how can we say that it happens on the load time only? I mean,
Right. So no, that's why I mentioned, right. So in not just recursion. Say you say like function one is calling function two. This is calling function three, and say your initial stack pointer is 1000. It the and within function tree you are accessing a name, like a variable name. So in that case, this name variable is present on the stack means this would be the offset would be with respect to whatever the stack pointer is at the beginning of this function f3. And usually in functions, right, you would be allocating a part of the stack, like it's called as like a stack frame. So whenever your function starts executing, right, there is something called as like a prologue, which your compiler inserts the code. What it will do is by default it will just minus the stack, so the stack grows upwards or downwards, right? So based on that, it will allocate some space on the stack pointer, say add esp minus 10 or something, so 10 bytes would be allocated. And now once the function,
my question is this. I mean, you're saying that the stack is actually varying as the execution of the program proceeds.
yes.
So it should be, I mean, why you're saying that it's load time binding, not execution time binding?
No, it can be both. That's what I meant, right? Like if you know, like these three functions are only called in this order, you can look at your code. Okay.
Okay, so it depends on the program
Yeah, it
basically.
depends on the program. That's what I mentioned. So like in your, if the code is like this, it is at the start of every function, it will be allocating some space for in the stack for use by that function. So if you know the initial stack pointer or something, you can just, and if you know like in this order only these functions would be executed, you can very well just add and subtract and find out where this name variable would be stored.
Okay, okay, got it. Thanks.
So yeah, so in those cases load time is there, and then cases where you mentioned like recursion or the call graph is very complex, right? As in f1 calls f2, f2 calls f3, f4, like it's very complex. Then it is not feasible. Like we just execution time binding, we can just tell it. That's it.
I mean, my question was that because when there is a long tree of that function
Yeah,
calling,
yeah.
so
So
then
if
it
it's
would.
like very long, right? Like you can do static analysis, you can do, but it won't be that feasible. Like, you can just tell it execution binding.
Okay, thanks.
Okay, right. So if yeah, so detailed explanation. So for question 4, the correct answer is option D, all of the above. If no doubts are there, then we'll move to question 5. So external fragmentation exists when, in which scenario? When there is enough memory to satisfy the request, but it is not contiguous, or when there is a request cannot be satisfied even when the total memory is free, or a total memory is insufficient to satisfy a request, or none of the above.
A.
Yes. Option A. Any other guesses? B, C, or D? Right. So the correct option is option A. The other options are wrong. So option A is the scenario. Say like you have uh, say these are all used, and this is 10 bytes, and this is 100 bytes. And now if I want to allocate some memory of 110 bytes, you cannot allocate because this 10 and 100 are split. It's not contiguous. So this is because of external fragmentation. Option B is something where say you have um, whole this whole thing is like 100 bytes, and you're requesting 200 bytes, then it cannot be satisfied. So that is option B actually. And option C is a total memory is insufficient, right? So same as option C actually. So option B and C are same, it's rephrased. So the correct answer is option A. This is the case when external fragmentation scenario exists, right? Any doubts in this question? If not, we'll move to question 6. Which table contains the base address of each page in the physical memory? Is it the process table, page table, memory table, or none? None of the above. Sorry? Can you repeat? Okay. Nandan mentions page table. Sajikant, you are mentioning something. Right. Uh, the correct answer is page table, as Nandan mentioned. So, page table is the correct answer. Process table just stores information about all the active processes and all the processes irrespective of active or sleeping. So, all the processes it stores dimension. Page table is the one that stores it's with respect to each process, the page table, and the page table will contain the mapping of the virtual to the physical addresses of each page. So the page to the frame mapping that would be stored in the page table. Memory table, there's nothing like memory table I've heard of till now. So A, B and D are A, C and D are wrong. Option B is the correct answer. Any doubts in this question? Right. If not, we'll move to question 7. What is compaction? Is it a technique for overcoming internal fragmentation, or is it a technique for overcoming external fragmentation, or is it something related to do with the paging technique, or none of the above?
I'm not sure, but is it A?
Okay, Shashikant tells option A. Any other guesses? Nandan, any guess you want to try? Right, option A. So the correct answer is option C. So compaction is used to overcome external fragmentation. Say, you know what external fragmentation is. We had seen in the previous question. So the same scenario, right? So your there is like 10 bytes free, and there is 100 bytes free, and you are requesting 110 bytes. So now your OS or the OS or something, what it can do is it can very well just transform this whole mapping into something like totally this is these two regions are merged, right? These two regions are merged, and this 10 and 100 are contiguous in nature, and it becomes 110 bytes. So it just compacts all your memory. So what it will do is it will just go through a pass, like a linear pass, and it will just get all the allocated regions present in that memory, and it will keep all those allocated regions together so that in order to overcome this external fragmentation. So this compaction, it can be done, say, like, you know, not for every memory request, but say if the OS cannot handle a specific memory request. Say in this case 110, when it requests the memory, it cannot 110 bytes are not free, but the total memory is something like equal to 110. So in that case it will trigger the logic for compaction in order to um, uh, just allocate or reallocate all the allocated regions, remap those allocated regions and keep it together, and get the total memory, the total freed memory contiguous, and then satisfy that specific request. So that's what compaction is all about. For so compaction can happen in whether paging is there or not, right? So in just segmentation or something also, the compaction logic can be included. So this is even in segmentation there is the concept of external fragmentation. Even in paging there is external fragmentation. So in all these techniques compaction can be included, but it is not a technique for overcoming internal fragmentation, because once you get the notion of like a segment or a page table, right? So once you get the notion of, say, like a minimum allocatable region. So for pages means it is 4K. 4K is the size of the page, and for segments, say it should be minimum of some 32 bytes or something like that, right? So in that case, if you want to store a variable of size just 1 byte, so in that case the remaining space would be wasted, but still you have to use that whole segment or that page. uh, so in that case, whatever wasted space is there as part of that segment, that is what refers to internal fragmentation. The reason why internal fragmentation is difficult to avoid is because uh, for, for maintaining these segments and pages, right, you need to have this page table and segment table and all these things, right? These are all like overheads, because you will be utilizing some memory and the logic to traverse the page table, segment table for each memory access. Now if you want to track, so these page table and segment tables are used for tracking where your pages are and segments are. And if you are now if you want to avoid internal fragmentation completely, then you have to track every single byte which is present in your memory. So for tracking every single byte, imagine how much of overheads you would be using. So say you have a 4 GB RAM, then for every byte in that 4 GB, you would be having an associated entry, and that entry itself would be 4 bytes. Like assuming it to be like a 32-bit address, right? Then for every 1 byte entry, like each address points to a byte. So and each address is 32 bits, assume it. So 4 bytes. So for every byte, you would be having a 4 bytes entry, and storing this metadata itself, right? So 4 GB into 4 bytes. This itself is greater than the total memory space actually. So it's greater than 4 GB. So to avoid this overheads and all these things only, designers try to have a set segment size or a page size or some minimum allocatable region, have a limit, so that the overheads used for storing this segment table and the logic for tracking the segments, etc., is like a trade-off. They decide the segment size and page sizes all. So internal fragmentation cannot be completely over ruled, or it cannot be completely solved, because you have this overheads problem and all these things. But external fragmentation, you can very well solve it easily by using compaction and all these things. So any doubts in this question? What is compaction? If not, then we'll move to question 8. Which address is generated by the memory management unit? Is it the logical address, physical address, or absolute address? Right. So Nandan mentions D. Sashikant, any guess? So the correct option is option B, physical address. So a related question we had seen previously, which address was generated by the CPU. That one was the answer was logical address. This is just the extension of that question with respect to MMU. The MMU is the one which generates the physical address by traversing the segment tables or the page tables and all these things. So option B is the correct answer. I guess no doubts in this question. Let's move to question 9 then. Yeah, it's an easy one, I guess. Yeah.
Power of
Sir, could you also
Sorry.
graduate
C is
level
the answer. Power of
I didn't hear you. Sorry. Sashikant, were you telling something? So the size of page, yeah, as Nandan mentioned, it's always power of 2. Like that's the obvious answer. So, right, the option C is the correct one. Okay. Right. So let's move to the last question. Okay, this one was also easy. Logical address space is divided into what? Partitions, frames, or pages, or none of the above. So Nandan's mentioned like option B. That's the correct answer as mentioned by Nandan. Pages. So your logical address will be pages, and the physical address would be frames, and your page tables would be uh, having the page to frame mappings. Right. So this is so option B is the correct answer. The other options are wrong. Right. So in that case, we have discussed all the 10 questions. So that's the end of the session. Then, do you have any other doubts or in any of the questions or anything? Yes, Nandan.
Like my question is that in the concept of the base and limit,
Okay.
uh, what is the criteria for setting the limit? Is it same for every process, or uh, for different for every process limit?
Okay. Nice question, Nandan. So, question is, what's the criteria for setting the limit? Um, setting the limit. So, you can. So what's the main? So I'm just answering it based on my understanding. Right? So mostly the operating system would be setting the limit, right? Um, because while executing and while loading the process, it will be setting the limit. And what limit it would be setting is um, so say like if you have gone through your okay. So assume like the whole process as such has just one base and limit, right? Like not going segment wise. Segment wise also it's applicable. So just the say process P1 has the base and limit. The limit will be say something whatever at the load time it will know what's the size of the code space, so it will include all the libraries and all those things. So the size of the code and the global variables or data, the data section, and also um, it will have a limit for the heap region also, and all these things, heap and stack region, right? So the stack region will be default for all the processes. So by default it will be allocated, say, 4 KB or something, like some amount it will be, by default it would allocate. And for the heap region, it it would be like inactive at that moment, like unless you invoke a malloc call, the heap region won't be active. So the sum of all these things or something close to this would be set as the size required, the limit thing required by your process. And the two uses of limit are, this limit would be one for security reason, right? So that your process doesn't access some other processes values and data and doesn't corrupt those. So that is one reason. And the second reason is, you can very well, like, I need not say like the OS has some, based on some heuristic or something, it knows for sure that whatever program I'm using or something, it don't use more than say 1 GB or something. And in that case it can just blindly set your limit as 1 GB. But the thing is, say multiple processes are there, and some processes are just using 1 MB or something, the other processes are using more, and multiple processes are there to efficiently allocate memory and all these things. If the limit is like realistic and close to the actual limit, right, the actual memory limit whatever the process uses, then it can efficiently utilize all the memory space and allocate to different processes. So this is what I guess happens underneath when you want to set the limit. And the limit can change also in my, because say your like a recursive function or something, your stack keeps on growing, or you want to allocate more region and you want to have more, you do more mallocs or something, and your heap region has to be increased, and your limit is just this much only. So in that case you have to do some system calls like mmap, or not mmap, but mmap you can do, sbreak or something, right? I guess in Linux. So if you do this sbreak or something, it will go do a system call and it will increase the limit or something. So if there is the condition that all this memory has to be contiguous, then it will change its whole memory space to some other segment or something, segment as in some other region, so that the extra memory is also attached, and all these things are contiguous, and your base would be changed and the limit also would be changed. So all these things happen underneath. Does this answer your question?
Yes, very much.
Okay, thank you. Nice question, and then even I have not thought of these things actually while studying. Yeah, nice. Um, um, are there any other doubts in this, in the questions that we discussed? Thanks, Nandan. Sashikant, do you have any other doubts? Okay, take it as a no. So in that case, thank you everyone for attending the session and making it interactive. Thanks a lot. See you
Thank
in
you.
the next session.
In the next session, we will going to